So I'm going to talk a bit about this paper we did. It's going to move automatically. We'll work with that. Yeah, biologically inspired visual working memory for deep networks. All the code for what we do is on GitHub. I think it's reasonably Googleable, so I won't dwell on it too much. But attention and memory have this really kind of fundamental link. They both seem really relevant. It's one thing to look at a sequence of things and to break down our visual stimulus into a sequence of things. It's another thing entirely to effectively collect information out of that sequence, to aggregate it in some meaningful way. Well, there's a class of models that try to do visual attention. They let the model address an image by looking at a sequence of parts of that image and break it down. But what they tend not to do is really model memory in any kind of meaningful way. And we're going to have a look at that, and we're going to try and come up with a memory mechanism that we can use and apply this to these models of visual attention and see what happens. Okay, so how do we do memory? Well, fundamentally, doing memory, we're going to need some kind of plasticity. Okay, in the brain, as I experience things, my synaptic efficacy, the weight of connections changes as stuff happens, and it changes according to some rule. Well, thankfully, someone some time ago came up with a pretty simple rule that kind of models this, called Hebbian learning, often characterized by this phrase, neurons that fire together, wire together. What does it mean? It says that if I have two neurons that are connected, and one neuron fires according to some stimulus, and then subsequently my other neuron fires, then I increase the connection between them, I increase the weight. Otherwise, I decrease. Well, some guy called Rosenblatt, who kind of invented this whole thing in a way, he had some stuff that did this. So this was before backprop. They needed some way of having learning in connectionist systems. Well, he came up with something based on Hebb's rule that could do this plasticity thing. The problem is it's non-differentiable. I can't differentiate through it, which means I can't use it in a deep network. I can't train it with backpropagation. Why is it non-differentiable? Well, it's continuous time, which is a bit of a difficult thing to model in computers anyway. And it uses discrete activations, which means the gradient is always either 0 or infinite, which I can't do anything with. So what do? Well, we come up with a kind of differentiable relaxation of this. It's very simple, really. All it says is that I've got some weights matrix. The weights are the linear length. And I update these weights according to some learning rule. And my learning rule is inspired by this Hebbian learning principle. Once I can do this, I now have something that does unsupervised learning based on its inputs. As a sequence of inputs is presented, I'm adjusting these weights, I'm learning from that stimulus, I'm having some kind of dynamic nature to my network. Okay, so that's memory. How do we do this visual attention thing? Well, attention in deep networks is kind of a broad topic at the moment, and it has a lot of definitions that people use. In essence, it's something quite simple. Typically, I have some kind of sequential model where things are moving from layer to layer. In an attention network, in some kind of attention mechanism, I have some kind of spur on this. I have something that says, based on this input, decide what transform to apply to it, and then do it. So I have a kind of little skip connection type thing here. And what does it do? Well, it applies some kind of transform. I get to choose what that is as the network's designer, as the person making the architecture. My hope is that that transform is going to learn to focus on relevant information and then disregard irrelevant information. So if I was just applying a weighting to some vector, I'd hope that it's going to increase the weighting on things that are important and decrease otherwise. In visual attention, I hope it's going to choose the part of the image that's relevant to the problem I'm trying to solve. Okay, so how do I do this if I want to do it in a recurrent setting? Well, I just acknowledge some stuff. Right? I acknowledge that RNNs exist, and I can use them to do things. I acknowledge that I have attention mechanisms, and I just go, right, I combine them. So I now have a model which takes my image, decides where to look, goes through a recurrent thing, decides where to look next, goes through a recurrent thing, decides where to look next. And it keeps doing this until at some point I try and get it to do a classification or some kind of task. Ideally, we'd have gradient through all of that. In this particular paper that they did, they don't have gradient because they used a thing called hard attention, which is non-differentiable. They just extracted the pixels they want. So what do? They use reinforcement learning. And then some kind of clever people came along and said, well, what if we swap that out for something we can differentiate through? We can use interpolation to model affine transforms. So I can model the space of affine transforms of an image. My attention mechanism becomes something that says, here's my 6 affine coordinates. Use these to do something. What does it do? It extracts that region of the image. It can skew it, it can rotate it, it can scale it. That has a kind of relevance because that brings us a bit closer to what I might think I do when I look at images, right? I tend to move around as well as being able to just address a different part of the image. More importantly, it's now differentiable, so now I don't need reinforcement learning. I have this model, I allow it to glimpse several times at this image, break this image down into sequence, and at the end of it, I ask it to produce a classification. By training it end to end, so just training it to classify, I hope it's going to learn some kind of attention policy that addresses the image in the right way, that learns to look at the image and understand what it's seeing. Okay, so we've got that, some kind of nice attention mechanism that makes sense. We've also got some kind of memory mechanism that we can use. Well, what do? Well, we just put them together, right? I take my attention mechanism that we had before. This is pretty much the same image as that one we had before. But at each time, as well as going through this RNN and saying, okay, where am I going to look next, where am I going to look next, I also send these features through my memory network. This is an associative memory, works kind of like how we might primitively think the brain does things. I now have the ability to build up this memory representation. So yeah, okay, I can look at my image and I can learn some kind of sequence, but I also have a memory, and that becomes key. But I've got this memory and it's now some weights of a layer which is a bit intractable to use. How do I use it? I need some kind of query. I have something that says, based on the problem I want to solve, how do I get my latent representation that I can then use to, for example, classify? Well, classification is easy. So I project my query through it, a single layer, some kind of NLP, to produce a classification. What if I want to do something more complicated? Well, we're in the interest of trying to do things that behave like humans do. Well, what's something that humans do that's quite nice? Well, what about drawing? What about if I want to, as well as addressing an image with a sequence of glimpses, I also want to produce a sequence of sketches, where each sketch corresponds to a glimpse? Well, I can do this quite easily. I can get my latent representation. I can pass it through this thing, a transposed CNN, that gives me some sketch. In other words, it upscales. It takes my small low-dimensional thing and turns it into some image patch. I can ask my attention policy, which was already telling me where to look, where do I draw? I can then put this all together and I end up with something that at each glimpse also produces a small sketch. And after many series of sketches, I will end up with an image. We use a variational approach, which will become relevant later. All this means is that I have a space and I can sample that space and I can use this as a generative one, which becomes interesting if my sketches become interesting. So if I end up with something that's producing meaningful sketches, I also get some kind of meaningful generative one. We also need something to combine those sketches. So the sketches have a sequence. We need some way of deciding how to overlay them on top of each other. For this we use alpha composition. So we let each sketch also have an alpha channel. And we use that alpha channel to decide how to lay these things on top of each other. So that they don't overlap, right? The sum of two images isn't an image, so I need some way of overlapping them instead. Okay, so how does it do? Classification, it does all right. It classifies on MNIST pretty well. It beats the previous attention model, so there's something in this memory thing. Purely adding this memory, suddenly we get a much better result. We can use it to do self-supervised stuff, which becomes much more interesting. Because I can learn a network that draws things, and the way it draws things is by breaking them down into meaningful parts. If I use that representation to then learn some kind of classification in a self-supervised setting, I suddenly have a much more meaningful unsupervised representation. So we get something like, I don't know, top 5 and this self-supervised last time I checked. But what about if I do something like painting? And what about if I take a data set where I know that there's a lot of structure in the data? Something like Celeb A, this is a bunch of pictures of faces. This is when weird stuff starts to happen. It now learns a representation that goes from drawing backgrounds to then drawing parts of the surrounding regions of the face to eventually just drawing the face at the end. So rather than trying to draw the whole image in one step, it addresses it as a sequence and ends up drawing just the faces. Because of that, we can use it as a generative model. We can use the part of the region that represents faces to draw random faces from our distribution. But what about if we go a step further and say, well, look, I've got here some drawing that just represents the face. The very last drawing is just the face. And it's got an alpha mask. Well, that means that I can use it to do something like segmentation. So instead of multiplying it with the sketch that I was doing, I multiply it with the original image. We end up with something that actually is unsupervised learned to segment images of faces to just the face. without ever being asked to. At no point did we say, here's a loss that says you should segment it. At no point is there anything other than a loss that says you need to draw faces. But purely because it's attentional, purely because it has a memory, it learns to segment them at the same time. What about if we go even weirder, and we ask something to do two things at once? Remember I said we could project a query through? Well, that means I can project two queries through. I can get two different link spaces. That means I can train a model that both classifies and draws at the same time. This model gets about 1% error on MNIST. We're looking at, on the top row, a sample of its drawings for things that it misclassified. The second row is the misclassifications that it gave. Third row is what it was looking at, and the fourth row is what it should have classified. Well, now we end up with something we can start to infer, specifically because if we look at something like the far right example, we were looking at a 7, classified a 2. Normally we'd see that as just a mistake. Well, in this case, it also drew a 2. And we can start to understand perhaps why it's misclassified this time. In this case, I can see that it's simply neglected to notice the particular sharpness of the 7, and it starts to see it as a 2. It's just done some blurring. So maybe this helps us build in more robustness into these models as well. Okay, so to summarize, we took these visual attention models, we took this notion of a differentiable memory, put them together. We use that to perform things like drawing in a way that's much more interpretable for a human, and much more natural for a human. And it not only works better than previous attention models, but some things happen that we never asked it to do, we never predicted would happen, that just come out from having a model that does things in this way, suggesting there's something interesting in the nature of how we process images, and that that's maybe part of what constitutes our human visual intelligence. Thank you.